Hi everyone, my name is Leo Beltrachini. I'm a lecturer in the School of Physics and Astronomy at Cardiff Uni, and I work in the Cardiff University Brain Research Imaging Centre, Kubrick. And in this talk I will show you briefly what we do as physicists to understand the brain a little bit more, and why physicists are crucial in this quest of understanding the brain. So this is a brain. This is an amazing organ. This is so complex that allows us to be humans, to think, to feel, etc. It's a very complex system, as you may recognize. In fact, I would say that it's the most complex system that we may know of. Although we all have one, we don't understand it in detail at all, so we don't know how it works and how it looks like. And this is what we want to address in neurosciences. And in our jargon, using very specific jargon, we say that we want to characterize in general in neurosciences the way it works, this brain works, or every single brain works, and the brain they look like. And we say that we want to characterize the function and the structure of the brain. And this is basically, in rough terms, what we want to do, or what we do in neurosciences. Before going into more detail what we can do in physics to answer these questions, it's interesting to see why it's important to study the brain. So there are lots of different answers to this to this question. Some of them could be just because it's a complex system, it's so complex and we want to understand something complex a little bit more. But there are also lots of different practical answers to this question. For example, to diagnose diseases in early stages. Nowadays, there exist lots of diseases are recognized which are having more impact in society, which are called degenerative diseases that have an onset in the brain and, of course, affects the way we live. An example is dementia or Alzheimer's disease in particular, a disease that we are very familiar with. So we hear, we know that many people are having this condition, this syndrome, and it affects the lives of people. So people with Alzheimer's disease, they will have inability to do or to perform some everyday tasks like related to memory. Here in this picture, what I show is a healthy brain and an Alzheimer's disease brain, and you see that they look different. And the Alzheimer's disease brain basically changed its structure because of the disease. And what we can say is that the structure of the brain changed. And it's very important for us to find out the moment when the brain goes from the healthy stage to the disease stage. And the sooner, the more effective the treatment will be, and the better will be for the patient. As I said, this is a structural change in the brain, but the structural change is related to change in the function of the brain, and therefore it's very important to characterize this huge system, the brain, from different perspectives. So maybe studying the structural change will lead us to tackling or to more effective treatments of a disease that will have a functional change in the patient. So structure and function are basically two properties of this system that are tightly linked. And what is the problem in studying the structure and the function of the brain? Well, the problem is that the brain is inside the skull, and therefore we don't have direct access to these brains. And in the past, what people have done are basically to have invasive procedures. So these procedures could be first to open the skull and to see the brain and to measure the brain and to put some sensors and measure the brain activity, for example, the electrical signaling of the brain. I will talk about this a little bit later, or to see how it looks like. But as you may recognize, this is an ethical if we don't have strong reasons to do it. And we may have strong reasons to do it. For example, patients that have to go through surgery, for example, for a tumor or for epilepsy. But this is not good for understanding the brain in normal stages. For example, how the brain develops with age. So another option is to wait until the person is dead. But once the person is dead, there is no functioning, there is no blood flowing, there is no signaling, and therefore we are missing a very important part of the brain. So what we aim is to characterize both structure and function while the person is alive and without doing any harm to this person. And we say in our jargon that we want to do this in vivo and non-invasively. And neuroimaging is the answer to this. Neuroimaging is this discipline that consists on studying or characterizing, in particular, brain structure and function by measuring different physical processes that are happening inside our heads. Physical processes are many. For example, there are electrical signals, currents flowing throughout our brain. These currents generate an electromagnetic field, and we can measure some outcomes of this electromagnetic field, for example, electric potential on scalp. And therefore, by measuring this phenomena, we may say something about the brain function or structure. Other phenomena could be the blood that is flowing throughout the brain, or also that our brain are full of water molecules, and we may explore this fact to extract information of this system. And this is what we do in Kubrick. Kubrick is a synonym of neuroimaging, so it's a brand new center that we moved recently. Is one of the largest neuroimaging centers in Europe, and we have lots of different people from different disciplines, like myself being a physicist, and working in lots of different ways to characterize the brain, either functional structure or both. And for that, we have lots of state-of-the-art machines to look at brain structure and function from different perspectives, all of them providing complementary information. And everything under one roof. What I will do now is just show you some of the things we do, in particular with some of the machines we have there, which are called magnetic resonance imaging scanners, and why they are so important. They are magnetic resonance imaging, or MRI, are big machines, expensive machines that allows us to characterize the brain in a unique way. They look like this machine. And this is, for example, a 3 Tesla magnetic resonance imaging scanner that allows us to measure or to characterize the brain structure and function. How it works? Well, basically, what we do is to place the subject inside this ball. Inside this ball, this magnetic resonance imaging scanner generates a huge magnetic field aligned to the ball. And therefore, we can study responses of the magnetic moments of water molecules and understand the surrounding media. They generate, after a long process, of course, images like this. This is a cross-section of the brain obtained with an MRI, where we did not do any harm to the subject, and provides us with lots of different information, a huge structural detail. We can see lots of different tissues, and therefore they are exquisite to clinicians. How can we obtain this in a bit more detail? So, brain is full of water, and each water molecule will have a magnetic moment, like a compass. And when we put them inside the scanner, given that they are forced or they are surrounded to a very strong magnetic field, they will be aligned. And there is a net magnetization that is being created. Then what we do in MRI is to perturb the system by injecting some radio frequency pulses. And then we move this net magnetization. Once we stop injecting this energy, the system will go back in alignment with the main magnetic field. And in this going back, there are some signals generated that we pick we work with and allows us to obtain this beautiful image. Images that are of huge value to clinicians. But there are always questions about how can we improve these images. Can we improve the resolution of these images? How can we do that? And the answer is yes, we can do that if we increase the field that these machines generate. We have in Kubrick 2 of these 3 Tesla magnetic resonance imaging scanners. These are the most common scanners. Let's say they are clinical scanners that you may find in hospital. But can we increase the field? How, at which cost? So it can be done, and that's why we have in Kubrick this machine, which is experimental machine, so it's a research-only machine, which is called a 7 Tesla MRI scanner. So a scanner that has more than twice the field strength than the previous one. It's far more expensive, and there are only 5 in the UK, so they are research-only facilities. But they provide quite nice results and very informative results, in particular to clinicians, like shown in this picture. So comparison between some images obtained with a 1.5, a 3, and a 7 Tesla scanner. And you can see that the 7 Tesla scanner, for the same amount of time, is providing now us with more rich information. Or in this example, a slice like this, where we are highlighting the hippocampus, a part of the brain that is very deep, and it's very connected to Alzheimer's disease in particular, because it's responsible for memory tasks. So with the 70, we get details or level of detail that we cannot get with other modalities in a feasible amount of time. Of course, this is not for free, so we have a lot of problems that we work on, and these problems are about registering the images and avoiding the movement of the person to impact on these images. These images are, or could be, or could have a resolution of about 1/4 of a millimeter. So we need to register these images, because it's impossible for the subject to be still for 1/4 of a millimeter for, let's say, 20 minutes. So there's a lot of processing of these images that we do and we develop within Kubrick. But as scientists, of course, we have always a wish of going further. And how can we achieve a higher resolution? What does it mean to achieve a higher resolution, to get more detail than 1/4 of a millimeter? Well, that would mean basically to go to a level of detail of the cells. So the brain is full of cells. Most of them they're called neurons, but there are many other cells. And they are very small structures. And it would be amazing for us to characterize changes at this scale, so this micrometer scale, because the sooner or the smaller the scale, the sooner we will detect this eventual disease or eventual change in the brain structure. Maybe when we find out a change in a millimeter scale, it may be too late. So characterizing cells with non-invasively without doing any harm to the subject seems like science fiction, but physics tells us that this can be possible. Using diffusion processes is very complex but very well understood a tool in the physical sciences. To understand these small structures, it can be shown that we don't need a huge magnetic field, but we need a huge gradient of the magnetic field. Any system in the world, including 70 that I showed you before, have between 14 and 60 millitesla per meter, and they are shown to be not enough. But that's why we have this machine in Kubrick, which is the connectum scanner, which is 3 Tesla, but the gradient is 8 or between 7 and 8 times higher than any other system in the world. So this system was very complex to build, and at peak power it consumes 24 megawatts, which is the same as a nuclear submarine. And at the time of installing this in Kubrick, it was the second in the world. Nowadays there exist only 3 working systems in the world. And they can give us, and this system can give us lots of information about the cellular structures of the brain, as shown in this picture. For example, different slides like this, where we see radii, so the mean radii of the axons of cells that belong to the white matter, which is quite an amazing piece of information. The image is not so stunning, but that's why I have also a video produced with data from the connectome scanner, where we can see the reconstruction of the white matter of the subject. This is the white matter consists of all these wires connecting the brain, different parts of the brain, and making the brain works as a super complex system as it is. And with diffusion MRI in particular, using the connectome scanner, we can obtain super rich information. We can obtain parts of the brain that looks that not healthy or look unhealthy, and we can dissect. We can do any kind of anatomical studies that we want, again, without doing any harm to the subject, without being invasive. And this is the amazing side of medical imaging, and in particular magnetic resonance imaging. So, in conclusion, the physical processes are crucial for understanding the brain, to performing in vivo brain studies, and physics is crucial also to understand these physical processes and measure them, and by measuring them also obtaining some or characterizing this structure and function of the brain. And Cardiff University is a world-leading institution in this respect, with Kubrick being, again, one of the largest neuroimaging centers in Europe. Thank you very much. Hope you have enjoyed the talk.